Thanks, Nigel. So yeah, good evening from Singapore and good morning and good afternoon to people around the world. I'm really excited to be here today. Thanks so much for joining. I'm Fabrianne Effendi, as Nigel has introduced, an Associate Solutions Architect at Amazon Web Services. Recently graduated from Nanyang Technological University with a double bachelor's degree in computer science and business. And today I'll be presenting to you my computer science undergraduate final project, privacy preserving graph-based machine learning pipeline with fully homomorphic encryption for collaborative anti-money laundering. This was done under the supervision and mentorship of Associate Prof Anupam and co-authored with Prof Anupam. This paper has also been accepted for the 14th International Conference on Security, Privacy, and Applied Cryptographic Engineering, or SPACE 2024. So here's the agenda for today. I'll begin by giving you a background on the money laundering problem, graph-based machine learning, and privacy-enhancing technologies, followed by a deep dive into homomorphic encryption and zooming into fully homomorphic encryption over the torus. Then followed by the solution itself, which comprises two key pipelines, a privacy-preserving graph-based XGBoost pipeline and a GNN pipeline. And finally, some key takeaways and conclusion. If you have any questions, you can write your questions in the chat box, and later at the end, we can take any questions that you can have. With that, let's begin. Money laundering is the process of concealing the origins of illegally obtained money generated by criminal activity to make them appear to have been from a legitimate source. So there are three main stages in money laundering: placement, layering, and integration. So firstly, placement is when dirty money first enters this financial system. And one way this is done is usually by breaking down large amounts of illegal cash into smaller, less suspicious transactions. Next is the layering phase, where these illegal funds will go through a series of complex transactions and bookkeeping tricks to hide their origin. And one of the more common ways this is done is via a shell company network. So where money will go through like multiple shell companies, which are companies that have no active business operations, to hide their origin. And finally, the integration phase is where the now laundered money or clean money re-enters the financial system, appearing as normal funds from a legitimate origin. So this can be in the form of purchasing of luxury assets, financial investments, or industry commercial investments, just to name a few. So now that we've kind of understand what is money laundering, let us think of ways on how a criminal would design their transaction flow if they plan to money launder. So their web of transactions can usually be modeled in the form of graph patterns. So you can see over here, there's a list of some of the more fundamental graph patterns that this would comprise, where there'll be connections between the different entities and accounts. This would usually adopt patterns such as fan out and fan in, gather, scatter, scatter, gather, and so on, where each of these transactions and accounts will all be interrelated with each other. So these patterns facilitate the movement of the illicit funds, which pose challenges for banks to trace back to the true beneficiaries. So in combating these challenges, graph-based machine learning emerged as powerful tools. Graph-based machine learning, such as graph neural networks and gradient-boosted trees with graph-based input features, are able to effectively capture these graph patterns. They are able to capture the complex relationships between entities to identify money laundering patterns, providing real-time monitoring, scalability to analyze large-scale transaction data, as well as reduction in false positives, enabling investigators to focus on high-priority AML cases and improve resource allocation. So indeed, based on literature review that I've done, there have been a number of studies on GNN in financial crimes and gradient boosting models with graph features for anti-money laundering. But is graph-based machine learning sufficient for combating financial crimes? The answer is no, because currently banks' transaction monitoring practices are siloed. So they are contained to, for example, the individual financial institution or the individual jurisdiction. So this limits the ability to track transactions spanning multiple institutions and borders. And even with GNNs or graph-based machine learning, without these cross-border or cross-institution collaboration, there's only so far which graph-based machine learning can go because you're limited to the view of data which you have. To effectively combat financial crimes, cross-border and cross-institution collaboration is needed. But as I've mentioned, the privacy and security of banking data poses a legal challenge. So this is where privacy enhancing technologies and or PETs can come in. PETs like homomorphic encryption, local differential privacy, and federated learning enable secure data sharing and collaboration while maintaining compliance. One notable proof of concept is Project Aurora by the Bank for International Settlements. So it explores and compares different approaches in detecting money laundering activities. And what they found is that the centralized cross-border model that combines homomorphic encryption and local differential privacy performs the best in their various scenarios in detecting suspicious money laundering networks. This POC thus highlights the potential of privacy-preserving technologies in collaborative anti-money laundering. Hence, my research objective was to develop a privacy-preserving graph-based machine learning pipeline for collaborative anti-money laundering using fully homomorphic encryption. I'll now zoom into homomorphic encryption itself. Believe many of you will be familiar with it, but for those that are new, we'll be explaining what homomorphic encryption is. So basically, it's an encryption technique that allows direct computations on encrypted data without needing to decrypt it. So over time, various forms of homomorphic encryption have emerged, including partially, somewhat, and fully homomorphic encryption. And today we'll be focusing on fully homomorphic encryption, also because this is an FHE meetup. So FHE supports an unlimited number of both addition and multiplication operations, which makes it very versatile for various types of computations. In the context of machine learning, fully homomorphic encryption enables a party to encrypt the input data using a public key. And then the machine learning model will then be able to process the encrypted data without seeing the original data. So this keeps the data secure and confidential from the machine learning model itself. After which, the final result is also outputted in encrypted form, and the data would only be able to be decrypted by the client who has the private key. So this ensures the confidentiality of sensitive data, especially for, in this case, for financial institutions, paving the way for collaborative anti-money laundering efforts. So now I'll be explaining some technicalities of FHE. To guarantee security in FHE, random noise is added to the data before encryption. But this means that every time an operation is performed, there is a risk that this additional noise may overflow to the data, and then it will result in incorrect decryption. So in FHE, we have two main approaches to deal with this. The first approach is the level approach. So schemes such as BGV and CKKS tries to do just enough computation to avoid noise overflowing the data. Then the second approach is the bootstrap approach, like the fully homomorphic encryption over the torus. And this applies a special operation called bootstrapping to reset the noise to a nominal level, and this would prevent the overflow. But this leads to a trade-off when choosing a scheme, because either you could do a limited number of faster operations using the level approach, or an unlimited number of slower operations using the bootstrap approach. Now, programmable bootstrapping pushes these frontiers of bootstrapping. So first implemented in TFHE Concrete by Chilotti et al. So it's programmed to simultaneously evaluate a univariate function for free while reducing noise. And then this allows for efficient computation of complex nonlinear operations on FHE. So with many FHE schemes available for the my final year project, I focused on the TFHE concrete, where TFHE stands for Fully Homomorphic Encryption over the torus. So TFHE concrete was developed by Shiroti et al. And Zama and is the most comprehensive scheme. And it supports both leveled and bootstrap operations and was the first to implement what I explained earlier as programmable bootstrapping. It supports all kinds of nonlinear functions on both Boolean and integer data types. So this makes it a very good FHE scheme to be run with machine learning. And in this project, it will be implemented using the Zama Concrete ML Python library. Concrete ML is a Python machine learning toolkit by Zama that empowers data scientists to build privacy-preserving models on encrypted data, leveraging TFHE Concrete for secure machine learning inference. So it's data scientist friendly and can seamlessly adapt from classical APIs with a choice of built-in or custom models. Built-in models adapt an sklearn-like interface, and you can also build custom models using external libraries like PyTorch, Keras, and TensorFlow. So the solution for this solution, we'll be delving into the integration of TFHE using concrete ML with graph-based machine learning techniques. So this is something that has not been done in the research space before. And this will be divided into two key pipelines. Firstly, the privacy-preserving graph-based XGBoost pipeline, and secondly, the privacy-preserving GNN pipeline. So one is leveraging concrete ML's inbuilt XGBoost, and the GNN pipeline will be developing a custom concrete ML model. But before delving into these two pipelines implementation, let's zoom out a little. How would ML pipelines enable collaborative AML, anti-money laundering? So this is where I'm introducing to you the collaborative fully homomorphic encryption solution architecture. The process begins when a bank initializes the process with a query to the centralized server. It then forwards this query to all participating banks. Using fully homomorphic encryption, each bank encrypts the relevant data using the public key. And then this key is securely shared once, allowing for multiple transactions to be encrypted without repeated exchanges. This encrypted data is then transmitted back to the centralized server. And over here, secure machine learning computations are performed on aggregated encrypted data, and hence maintaining the confidentiality of the inputs. The results are then outputted back in encrypted form. And finally, the initiating bank decrypts the encrypted results using its private key, revealing only the output of the computation while keeping the confidentiality of inputs from participating banks. So this process aims to align with confidentiality regulations, such as those in Singapore, where the Banking Act prohibits the disclosure of customer information or the existence of a non-public relationship between the customer and the bank. So now we'll be moving on more to the implementation of this FHE for graph-based machine learning. To train machine learning models, we need data. But then real-world financial data are usually inaccessible due to the privacy of it. Hence, we turn to synthetic data sets for this project. And out of these synthetic data sets, there are three main in the research space currently. So MLDP, AML-SIM, and AML-World. And for the purposes of this project, AML-World dataset was chosen as it's the most comprehensive. So it covers like the various 3 stages of money laundering: placement, layering, and integration, and also models the various key patterns, models multiple banks, currencies, etc. But because of certain CPU limitations and constraints due to the still the computationally slower processes associated with fully homomorphic encryption, for the purposes of this project, had to reduce the AML world dataset size. So I created 2 modified datasets. for the first dataset, undersampling was used to create a balanced dataset. And then for the second dataset, random sampling was used to create an imbalanced dataset that more closely simulate real-world scenarios. So now that we have prepared the dataset, I'll be diving into our first key pipeline, the privacy-preserving graph-based XGBoost pipeline. And we'll be going through each stage of this pipeline step by step. Firstly, we'll start with dataset splitting. So this dataset splitting was done using a temporal approach. Transactions are ordered chronologically based on timestamps and then divided into approximately 80-20 train and test sets based on time. Transactions occurring before timestamp T1 are included in the training set, while those occurring after T1 are in the test set. And also transactions from the same day are grouped together. And this process prevents data leakage from future to past data and ensures that the model generalizes well to unseen data and enhances dataset integrity. Now, after data splitting, we employ the SnapML graph feature preprocessor to enhance the dataset with graph-based features. So developed by Lanusa et al., GFP, this graph feature preprocessor, efficiently extracts real-time features from graph-structured tabular data and is compatible with scikit-learn. So what it does is that it analyzes graph patterns for each edge in the input edge list, generating pattern histograms for feature extraction. And then the selected graph features include single hop patterns such as fan in, fan out, degree in, and degree out, multi-hop patterns such as what you've seen earlier, the scatter-gathers and different kind of cycles, as well as vertex statistics such as sum, variance, and skewness of transaction amounts. So you can see how from the train set and test set respectively over here, the graph feature preprocessor would then be able to create these graph features to create the enriched train and test sets respectively. So now that we've enriched our dataset with graph-based features, the next step would be to optimize our models, hyperparameters through Bayesian optimization. This systematic approach explores the hyperparameter space by iteratively assessing model performance across 50 iterations under different settings, guided by a probabilistic model of the objective function. So this allows us to select hyperparameters that maximizes the model's performance. And for optimization for this paper, we focused on 4 key parameters. So n estimators to determine the number of boosting rounds or trees, max depth, which specifies the maximum depth of each tree, learning rate to control the step size at each iteration, and call sample by tree, where it sets the fraction of features randomly sampled for each tree. And after Bayesian optimization, our optimized XGBoost then goes through this concrete ML pipeline for training and FHE encrypted inference. So for training, they will be trained first on plain text non-encrypted training data, but then after that we have to go to quantization, where these floating point values are transformed into integers in order for it to be compatible with FHE. Following which, a quantized model executes to assess FHE accuracy and determine the necessary modifications. This quantized model is then compiled into an equivalent FHE circuit, and finally, the quantized model executes on encrypted data once proper keys are generated. And this then is our entire privacy-preserving graph-based XGBoost pipeline. So just a quick reminder, if there's any questions, feel free to type in the chat, and later we'll address it during the Q&A. Now moving on to the results of this pipeline. On the balanced AML dataset 1, There's impressive performance with basic features with 99% accuracy, F1 score, precision, and recall. And because of that, the inclusion of graph features had little effect of the model's performance as it's already captured the relevant feature well. And the model also demonstrated consistent performance in encrypted inference, highlighting its ability to preserve privacy without compromising predictive performance. However, it's important to note that the significant overhead of FHE encryption, in which in this case, inference time is more than 100,000 times that of unencrypted data. But this was also done on CPU, and I understand that now there's also like the GPU implementation on concrete ML. So it will definitely improve these overheads. Then on the data set 2, which is the imbalanced data set reflective of real world transactions, this was, of course, there was lower F1 and recall scores because it's more challenging to identify the illicit activities accurately. However, the addition of single hop graph features led to improved model performance. Yet, introduction of more complex features like multi-hop and vertex statistics may slightly reduce performance due to potential redundancy, so performance is still better using the only basic features. So this highlights the effectiveness of incorporating graph-based features in improving the model's predictive abilities. Encrypted inference then maintained consistency in performance, preserving privacy without compromising predictive accuracy. And interestingly, as feature complexity increased, there was a decrease in the inference time and the time ratio. So this unexpected trend suggests that additional computational overhead introduced by advanced features may be offset by their ability to streamline the inference process, and this results in more efficient model predictions. So we've also conducted other experiments varying different parameters such as n estimators, max depth, as well as like n bits. And I think that was to the consistent conclusion was that there needs to be a balance between model performance and computational overhead when selecting hyperparameters or determining the optimization search space. And that's what we did using these various experimental results. So now I'll be diving into the second pipeline, the GNN graph neural networks pipeline. So for this pipeline, the focus is to explore the feasibility of making it compatible with fully homomorphic encryption, a challenge that has been little explored due to the inherent complexities of GNN. The process involves selecting a GNN baseline model, quantizing it to ensure FHE compatibility, training, running using the concrete ML, and then optimizing parameters and the architecture. So now explaining the details of this pipeline. For the GNN baseline model for this project, we've selected the graph isomorphism network, GIN, a GNN that learns node representations invariant to node NH labels. This was implemented using PyTorch geometric and adapted from Altman et al. And Benny Agassi et al. In order to make this GNN compatible with FHE, we need to quantize it, the GNN. So this is because the FHE, at that point in time where I was doing it, it was constrained to 16-bit integers. And so quantization will help this transform the floating points in machine learning models to integer representation. So for quantization, it was exploring different methods, and there are two main methods for quantization. So quantization-aware training, or QAT, quantizes right from the start. So it trains the model with awareness of quantization constraints from the start. Meanwhile, post-training quantization, PTQ, it quantizes after training in full precision. So that's the differences between QAT and PTQ. And eventually, I chose QAT for its ability to optimize its parameters in alignment with the demands of lower bit with weights and activations during training. So this leads to higher accuracy compared to post-training quantization, as the models was trained with quantization constraints in mind. And this QAT was done with the help of the Brevitas library, which allows us to map the PyTorch geometric layer and its activation function to its relevant quantized version. And then we configure the weight and bit width to its 16 bits integer precision. So after quantizing the GNN was trained and then compiled into its FHE equivalent. And as you can see, this compilation is actually a lengthy process. And this was where there was a lot of also like debugging, etc. to be done. So just on a high level overview for the conversion process, we'll be first going through this exporting this model to ONNX. So ONNX stands for Open Neural Network Exchange, and it's a open format for representing machine learning models, enabling interoperability and portability across different frameworks and platforms. So this ONNX model was visualized using Neutron to understand the various ONNX operators, inputs and outputs employed within the model. So you can see each there's for let's say the neural network model, the GIN model, there'll be all these various operations under the hood that was being processed. So after which, after exporting this model to ONNX, we need to check that all ONNX operations are being supported by Concrete ML. So if it's supported, then that's great. There's less work to be done. But if not implemented, then there needs to be implementation by modifying the Concrete ML library itself. So for example, during this project, the scatter elements operator was not readily available yet. So and scatter elements is a crucial operation for GNNs because of its ability to operate for efficient data updates within tensors and aggregating information from neighboring nodes in a graph structure. So in order to implement this, I was like doing various things to resolve this. So firstly, like submitted GitHub feature request issues and communicating with Zama on different ways you could go about these scatter elements. And then also referred to the ONNX documentation to understand scatter elements behavior. And finally implementing this operator by modifying the Concrete ML library itself. So this is on a high level the conversion process of the compilation of GNN. So just be going through the rest. But so something to take note is that for this project, so we're exploring the feasibility of the two pipelines, and for this GNN pipeline, there was still certain roadblocks in the full conversion of it, but nevertheless, it has set the foundations of like for future research works. So after checking that all ONX operations are being supported, it's supposed to convert ONX model to a NumPy module, quantize this NumPy module successfully, and then trace the quantized module to create a concrete op graph. And then after which, I'll do some validation and optimization of security parameters before generating the FHE machine learning code, machine code for FHE operations, and then resulting in the successful conversion of the GNN pipeline. So here, now we'll be elaborating on some of the key takeaways from this research project. So embarking on something novel is definitely challenging and risky as no one has done it before. And yeah, especially with zero precedence and little documentation. But we learn to persevere, to never give up, and don't be afraid of failure. And then also learned the importance of engaging with the open source community. So for this project was raising multiple feature requests and bug issues to Zama and ONNX. And then technical wise also, I learned the importance of like systematic debugging, and because through this project with the lack of also certain documentations for the integration of graph-based machine learning with TFHE, there was a lot of debugging to be done. And then because of that, my my debugging skills also significantly improved. So for some of the future works, it's over here. Firstly, for future works, we could look into improving the FHE performance, speed, and compatibility. So this includes refining the model architectures to enhance performance and speed during encrypted machine learning, and ultimately strive for full compatibility between the GNN and TFHE or Concrete ML framework. Also, can look into optimizing GNN compression, where more advanced compression methods can be done to further reduce model complexity and enhance efficiency. Also, scaling to larger data sets without compromising performance and looking into like more of the hardware acceleration side of things. And finally, collaborative initiatives such as engaging with the Zama open source community and the FHE community and contributing to the enhancement of the Zama Concrete ML library. In conclusion, it takes a network to defeat a network. So let us harness the power of a collaborative data network, graph networks in machine learning, as well as fully homomorphic encryption to defeat a financial crimes network and safeguard our financial future. So before I take questions, I'll just show the resources over here. You can scan this QR code or key in this link to access the research paper and also this link for the GitHub repositories to see the implementation of code. And yeah, that's for the resources. And if you have any questions, feel free to write in the chat. I'll be addressing it shortly.